due tomorrow, which is from 5.6. I'm going to skip past the evaluation and just move on to the derivatives. So I'm going to pick out some problems from the derivative. If you guys have any specific questions, I can also go over those as well. So this is from your homework, page 372. Let me start off with 42. Okay, find the derivative of the function f of x r secant 2x. Okay, so we have, let me remind us our derivative rules here for our trig. Okay, we talked about yesterday how these three main derivative rules for our trig, they all have similarities that we can kind of pull. They'll have u primes in the numerator. They all have 1 and u squared in the denominator. So the simplest looking one is the arctangent one, just the 1 plus u squared. Arcsecant is the most complicated one. It's got that absolute value of u. It's got the square root. And it has a minus sign between the u squared and the 1. It ends up being u squared minus 1. We talked about how the order helps. What helps me with the order is knowing that the u's are next to each other. So if arcsecant is u squared minus 1, then arcsine is very similar, but it's going to be a different order, 1 minus u squared. Okay, so arcsecant, we have our rule here. Our u value is the 2x, so I'm just going to follow what the rule says and get to my derivative. Okay, so my u value is 2x. U prime, 2x becomes 2. Absolute value of u, square root of u squared minus 1. Make sure you put a parentheses around the u value because we want to make sure that not only is the x squared, but the 2 is also squared. Okay, do some cleanup here. We can cancel out inside the absolute value bars, but whatever is left needs to stay inside the absolute value bar. And there's a 1 remaining in the numerator. And then I'm going to clean up that expression inside the radical there. Okay, let me try 43 here. So 43, find the derivative of arctangent of e to the x. Okay, we have the arctangent rule, which we're going to apply, but we're also going to have to need to use the e to the u rule. So as a side note here, derivative of e to the u is just e to the u times u prime. Okay, so arctangent of u's derivative is u prime first. U prime is we need to figure out the derivative for e to the x. And the derivative for e to the x is just e to the x times 1. So just e to the x. The divided by 1 plus u squared. So 1 plus u squared. Okay. Now, whenever I have two exponents next to each other, I'm going to be multiplying those together. Okay, so there's my derivative. Okay, let me skip down to 49. Okay, so a couple of things we have to be aware of. If we want to find the derivative, we have to recognize that there's a need for product rule here. The 2x and arc cosine x are two separate things here, so you got to go through product rule. And also, once I get this in parentheses, this is going to need chain rule. There will be an inside-outside portion here. Okay, so I'm going to just rewrite the equation here, get everything set up, and I'm going to apply my derivative rule here. So I'm just rewriting it, not doing derivative just yet. Okay, square root means I can raise it to 1/2. So we know there's product rule going on here. And then when we get to the chain rule here, there's an outside portion. And there's the inside portion that we got to take derivative separately, right? Okay, so let's set up product rule. Okay, f prime g plus f g prime. So g prime arc cosine of x. Arc cosine of x derivative is the same as arc sine. It's just there's a negative in front of the derivative here. So negative u prime over the square root of 1 minus u squared. My u value is x. So negative 1 over square root of 1 minus x squared. Okay, so there completes my product rule for my first term. Now I'm going to go through my second term, which will require chain rule. Outside derivative first, negative 2 parentheses to the 1/2. Go through power rule, bring down the 1/2, subtract 1 from the exponent. Okay, fill in the parentheses with my original expression. Times the inside derivative, 1 minus x squared derivative is negative 2x. Okay, so any questions there? Okay, we can do some cleanup here. Combine this together. Okay, so this looks like a mess, but I'm going to try to do some cleanup here. So the 2 and 1/2, they cancel out. That's nice. The two negatives cancel out, becomes positive. The 2x is going to be in the numerator, and the 1 minus x squared is in the denominator, and that 1/2 is really square root in the denominator. So what you notice is this actually ends up the same as this term, just different signs, which will allow them to cancel out to zero out. So that's my derivative. All right, any questions there? Okay, let's see, what can we do next? Let me skip down to 59. Okay, find equation of tangent line. Those are the directions here. So that means we need to have ordered pair and slope. Well, the nice thing is the ordered pair is already provided for us, so we can hang on to that. We can find the derivative. From the derivative, we can find evaluate the derivative at the x value, get the slope, and then put into point slope form. Okay, so order pairs already here. Let's go ahead and find the derivative. 2 arcsine of x, the derivative is u prime over square root of minus u squared. The 2 is the coefficient, it'll just hang out in front. And the derivative is just going to be involving that arcsine of x. Okay, so the 2 stays. My u value is the x, so u prime is just 1 divided by square root of 1 minus x squared. So there's my derivative. From the derivative, I can find the slope. So just insert the x value in. Okay, let's do some cleanup here. This is 1 minus 1/4. 1 minus 1/4, the same thing as 4 over 4 minus 1 over 4, which is 3 over 4. Okay. Looks like a complex fraction here, but I can, if I divide by a value, it's the same thing as multiplying by its reciprocal. So if I can bring that up, I can see how that can combine with that 2 above. So 2 times the square root of 4 over 3. I'm just taking the reciprocal there. So this is really 2 times the square root of 4 divided by the square root of 3. Okay, square root of 4 is 2. 2 times 2 is 4. 4 over root 3. There's my slope. I can leave it in that radical form, or you can rationalize it. Either way is fine. Either way, that's my slope. I have my slope. I have my ordered pair. Now I can do point slope form. So 1/2 pi over 3 gets inserted into the x1, y1. Slope is the 4 over root 3. There's my equation of the tangent line. Okay, any questions? Let me skip over to 77. 63 is a similar process. Well, we still have to find equation of the tangent line, but you just have to go through a product rule here to find the derivative. Once you get to that derivative, plug in 1, get that point slope form. Okay. Okay, let's try 77 here. This is implicit differentiation with equation of the tangent line. So there's my ordered pair. I'm going to find the derivative. From that derivative, I can isolate dy dx. Once I get dy dx by itself, that's basically my y prime. And then I'm just going to insert the x order pairs into the derivative to get my slope. And then just like the previous process, I'm just going to do equation of tangent line. It's just that the derivative requires a little bit more involvement here because the y's are kind of all over the place. We have to collect our dy dx's. Before we jump into our derivative rule here, we have to recognize the need for product rule because x and arctangent y are distinctly separate. Okay. Meanwhile, keeping track of our dy dx's. So there's implicit differentiation along the way as well. Okay, so let's jump into the derivative. The x squared is just by itself. That's easy. That's just 2x. Okay. Then we start our product rule process here. Okay, so f prime, x's derivative is 1. G function, no changes. Back to f. And then g prime, arctangent of y. So we want to apply the rule for arctangent, which is u prime over 1 plus u squared. So u prime, y's derivative is 1, but we're asking for y's derivative, so we need to attach dy dx there. Divided by 1 plus u squared, and my u value is y, so 1 plus y squared. Okay, so that completes product rule for that second term there. Equals, so we keep continuing our derivative process. Y's derivative is 1, but we're asking for y's derivative, so we need to attach dy dx. And then the 1 goes away to 0. Okay, so I'm going to try to collect my dy dx's here. So these are my dy dx terms. I'll put those together. So these are combined together. So put this all into one fraction here. Okay, so now we could isolate the dy dx by itself first, but we're really not after the derivative equation. We're after the slope. So as soon as I have my dy dx is showing up, I can start inserting my x value and y value in. Just I think that will kind of speed up the process in terms of cleanup. That way there's less variables to keep track of. So I'm just going to go ahead and start entering in my x and y values at this point. There's no need to hold on to all these variables if ultimately at the end they're going to be replaced with x and y anyways. Okay, so we just want to get to the slope here. So negative power 4 will replace x, and 1 will replace all the y's. Okay, so negative 2 times negative power 4 becomes 2 pi over 4, which is pi over 2. And arctangent of 1, this is basically saying, what theta value allow tangent to be 1. Okay, and we know that tangent is equal to 1 at pi over 4, so we can replace this with pi over 4. So we're getting closer. It's a little messy here, but here I'm going to factor out a dy dx. And this cleans up a little bit here. If I pull this up as 1/2, you can see this is really pi over 8, right? So let me do that cleanup here. So, or negative pi over 8. Okay, so if I factor the dy dx out, I'm going to just match common denominators here. And while we're at it, if I'm going to match common denominators here, I'll just go ahead and match common denominators here as well. So pi over 2 is same thing as 4 pi over 8. And pi over 4 is really 2 pi over 8. Sorry, not equals, times. Combine like terms here. 4 pi over 8 minus 2 pi over 8 is 2 pi over 8. If I want to solve for dy dx, I can divide by the fraction. Dividing by the fraction is the same thing as multiplying by the reciprocal. And that way I can get my slope value cleaned up. The 8's cancel out. So I'm just left with 2 pi over negative pi minus 8. Okay, so I have everything that I need. Okay. I have my ordered pair up here. I have my slope here. And now the rest is point slope form. let me switch over to doing some trig-related rates. So this is in your um, test review packet. And if you don't have one, you can kind of just follow along. I can also put up a link to that test review packet. The key is also attached inside. And I'll put it in the chat box. But if you're my student, you should have picked one up in class yesterday. Right? But if not, there's the link. Okay, if you can turn to page 15, well, I'm going to just pick out a couple of practice problems here. Okay, so this is number 3 on page 15 in your test review packet. The angle theta is increasing at a constant rate of 6 radians per hour. At what rate is the side of length x increasing when x is 6 feet? Okay, so angle theta is increasing at a constant rate. So we know this is related rates. Related rates, we're always going to have a d over dt involved, right? So there's always going to be time involved in our derivative, our differential. Okay, so it says angle theta is increasing at a constant rate of 6 radians per hour. So we know this is not just theta, this is time involvement here. So this is talking about d theta dt. Okay, increasing, so we know it's a positive 6 radians per hour. At what rate is the side length of x increasing? So we're looking for the rate that x is increasing. So we're looking for dx dt. When x is 6 feet. Okay, so we know that with trig-related rates, we're always having to start off with a trig equation. And the trig equation is either sine, cosine, or tangent. And we always want to involve one of the trig equations that will hit all the values that we want to have in our triangle. So we want to be able to find a trig equation that will hit theta, x, and 10. And the one that's best suited, it will be sine, right? Sine will allow us to hit that opposite and hypotenuse if we're looking at it from theta's perspective. So here's our starting equation, sine theta equals x over 10. Okay, we want to find the derivative, but to find the derivative, let's get that right side to be a little bit visually more friendly here. So I'm going to pull that 10 out as 1/10. Makes it feel more familiar. Okay, so now we can find the derivative. So remember, when we find the derivative, every variable gets impacted by time. So there's going to be a d over dt involvement there. So sine of theta becomes cosine theta, d theta dt. 1/10 x becomes 1/10. The x goes away, but we're asking for x's derivative, so time is involved there. So dx dt. Okay, so we're looking for dx dt. That's the unknown. D theta dt in this case is given to us. And then the one missing piece that we need to worry about is finding a replacement for cosine theta. And this is where we have to go to our triangle, build another triangle, fill out all the sides so we can find a ratio replacement for cosine theta. Okay, so I'm going to step to the side here and build a second triangle. and try to fill this triangle with numeric values along the sides. Okay, so I know the 10 is hypotenuse. X in this case is 6. And then Pythagorean theorem can help us find that third missing side. A squared plus B squared equals C squared. This is basically a multiple of the 3, 4, 5 triangle. So if you recognize that, then you can recognize that B is going to be 8. But if not, then we can work this out. Okay, so cosine of theta, based off this triangle, is adjacent over hypotenuse, right? So cosine of theta is 8 over 10, which I can reduce to be 4 over 5. So this is going to be my replacement for cosine theta. So we should have everything that we need. We have a replacement for cosine theta. We have 6 being d theta dt, and then we can solve for dx dt. We have one remaining unknown variable, which is what we want, that we can solve for that. Okay, so cosine theta is 4/5 times d theta dt is 6 equals 1/10 dx dt. Okay, multiply this out here, 24 over 5. Okay. Dividing by 1/10, the same thing as multiplying by 10. Multiply this out, or I can just reduce the 10 and 5, make it 2. Makes it a little bit easier. Rather than doing 240 divided by 5, I can just do 10 divided by 5 is 2. And 24 times 2 is 48. So dx dt is just 48. Our units of measure, x is in terms of feet, and t is in terms of hour, so feet per hour. Okay, let me do a few more here. So pick out some problems. Page 16. Okay, let's try number 3. I'm sorry, number 5. Okay, so a kite 40 meters above ground moves horizontally at a rate of 3 meters per second. Okay, so here's the kite. It's moving horizontally. So we can imagine that as taken care of by this horizontal segment here. I'm going to call this x for now. There's the theta. At what angle between the string and the horizontal is decreasing when 80 meters of string has been let out? So the string is here. The person that's holding the kite is down here. Okay, so this is our starting point here. The movement from that kite is going to be dx dt, and we can fill that in later, but this is our starting diagram. The movement that the kite is having, we can kind of track it the same way as we track this. So these are connected. Sorry. One thing I have to make sure is there's 80 meters of string being let out, but that is still a moving value, right? It's not going to stay 80 meters the entire time. You know, the string, you know, the kite is moving, the string is moving, but we want to find out this moment in time when that string has 80 meters of length out. So it's not going to stay 80 meters the entire time. You know, if the kite is continually moving to the right, then there's always going to be string being let out. So we have to let that be a variable to begin with, and then we can fill it in with 80 a little bit later, okay? But the way that this problem is moving, the kite is moving to the right, and there's going to be string continually being let out. So I'll use Z here to represent the hypotenuse. But the nice thing is that the kite is 40 meters above the ground. So that is a holding constant. So that's nice. So having that as a constant allows us to avoid quotient rule, because we just rely on either sine or tangent to help us get there. Okay, so I'm going to just arbitrarily kind of choose tangent here, because any three trig functions will work, but we want to be able to involve theta and ideally the 40, because if I can hold on to that 40, so I can either use tangent to involve that 40 or sine to involve that 40. Okay, so I'm going to use tangent here. Okay, so if I want to find the derivative, I have to get this ready. So I'm going to bring that x up to the top so I can get it ready for power rule, so I can avoid quotient rule. Okay, so now we're going to jump into our derivative here. Tangent becomes secant squared. Remember, this is related rates, so we need to attach d over dt. 40x to the negative 1 becomes negative 40 x to the negative 2. That's my power rule. And then multiply by dx dt. Okay, so let's do some cleanup here. Okay, so x, well, we have dx dt, right? Dx dt is the kite moving at 3 meters per second. But x is this moment in time when 80 feet of string is let out. So let me just go to the side here, build my second triangle, so I can kind of just start filling in all my numeric values, since I'm going to need it for my x as well. Pythagorean theorem, and also you can kind of recognize this as a special right triangle here. This is basically a 30, 60, 90 triangle, but we can work this out and see this is 40 squared plus b squared equals 80 squared. So 80 squared minus 40 squared. You know, that the math is messy here, but if we recognize this as a 30, 60, 90 triangle, and the opposite is half of the hypotenuse, then we know this must be the long leg, and long leg is going to be the short leg times √3. So we know this is going to be 40 √3. But if we work this out, we can see 80 squared minus 40 squared is √4800, and that cleans out to be 40 √3. Okay, so x gets replaced with 40 √3. dx/dt gets replaced with 3. And what we need to worry about now is that secant squared. Okay, so secant squared theta, we have to go to our triangle and find a replacement for that secant theta. Okay, so secant theta is hypotenuse over adjacent, so 80 over 40 root 3. Okay, so 80 and 40 can reduce nicely to be just 2 over 1, so 2 over 1 root 3. And if secant is 2 over root 3, then secant square theta is going to be squaring that, which is 4 over 3. So I have a replacement for secant square theta. So 4 over 3 times d theta dt equals negative 40 over 40 root 3 squared times dx dt, which is 3. Okay. Divide by 4/3, same thing as multiplying by 3/4. I'm going to see if I can 40 squared times root 3 squared, which is 3, times 3 over 1 times 3 over 4. Let's see some cleanup here. 3's can cancel out. One of the 40's can go away. So I'm just left with negative 3 over 40 times 4, which is 160. So d theta dt is always in terms of radians, radians per time unit, radians per second. Okay, why don't we do 1 or 2 more related rates here? Okay, number 6. Okay, so a man standing 12 meters away from a flagpole. It's always going to be a triangle. He holds onto a long rope attached to the flag as the flag is raised at a rate of 10 meters per minute. Okay, so raising is vertically, but we know it's moving, so we don't want to replace that with 10. We want to hold on to that variable because we know that that as that flag is rising, we know the height of this triangle is also increasing. The rope runs tautly through the man's hand so that it's always kept straight. Okay, so we know that this is also a variable. This is the rope is being let out. It will be a variable value. But the man stands 12 feet away from the flagpole, so this is remaining constant the whole time through. That's never changing. Okay. Find the rate of change of the angle between the rope and the flagpole. So that's up here, actually, between the flagpole and the rope. At the moment when there is 24 meters of rope between the flag and the man. Okay, so let's build our equation first. We can either use cosine, okay, or we can use tangent. I'm going to use tangent here. I think tangent will allow us to have that y in the numerator, just a little bit easier power rule here. But we could definitely use cosine as well. Cosine works, but I'm just going to choose tangent. And the reason that I want to involve that 12 is because I can avoid quotient rule. If I use sine, then I got to use quotient rule because both these values are, neither of them are constant. Okay, so there's my equation. I'm going to get this ready for my derivative process. Okay, so I'm going to, I don't want to stare at that 12 here, so I'm going to pull that 12 out in front, make it a coefficient, 1/12 times y. Okay, so now here's my derivative process. Tangent's derivative is secant squared d theta dt. 1/12 is going to stay, that's the coefficient, and the y becomes dy dt. Okay, so let's see what information that we have here. The flag is raised at a rate of 10 meters per minute. We know that is involving y, so dy dt. Positive, since that is allowing this triangle to be, the height to be increasing over time. And find the rate of change of the angle between the rope and the flagpole. So we're looking for, oh, I'm sorry, guys. Tangent of theta is 12 over y, right? My theta is up here. My bad. Let me scrap this and start again. Because my theta is usually down here, but in this case, they define theta up here. Let me try this one more time. Tangent theta equals 12 over y. Theta is opposite over adjacent. Okay, so this does require me to have to bring that up and go through power rule once that y comes up. Okay, so tangent theta becomes secant squared still. Power rule here, once the y comes up, negative 12y to the negative 2 dy dt. So here's my cleanup. Okay, sorry about that. Let's go back to gathering information here. So y, this moment in time, we don't know, but we can figure that out because we can go to our second triangle. 24 meters of rope between the flag and the man. So this is at this moment in time when the flag, when the rope is 24 feet long. So here's my second triangle. Okay, this is also a 3690 triangle because you see that one side is the short leg is half of the hypotenuse. So you can figure that this is going to be 12 root 3. But you can also do Pythagorean theorem to find that. Okay, so my y value is 12 root 3. Dy dt is 10. So the only thing missing, just like before, our work is going to be, what's different about these problems is trying to find that ratio to replace. Okay, so we need to find a replacement for secant theta. So secant is hypotenuse over adjacent. I know it's weird here that theta, we're usually seeing it down here, but it's up here now. So secant of theta is hypotenuse over adjacent to this theta here. I can reduce this, clean that up. 24 and 12 can reduce to be 2 over 1 root 3, which means that secant squared theta means I can just square my fraction, 4/3. Okay, put everything in this place, and then I can solve for d theta dt. And my y value is 12 root 3. Times dy dt, which is 10. So y squared is there, 10 Okay, I'm going to put everything on one side so I can get that d theta dt by itself and see what I can do to clean this up. So negative 12 over 12 squared times root 3 squared, which is just times 3. 10 over 1, and then 3/4 dividing by 4/3, the same thing as multiplying by 3/4. Okay, so everything's being multiplied and divided. I can just see what I can cancel out to reduce. One of the 12s can go away. 3s can go away. I'm just left with negative 10 over 48. That can reduce a little bit more. I can make it negative 5 over 24. Okay, and my units is radians per minute. Radians always for theta, and then time in this case is per minute. Okay, any questions? Yeah, I didn't quite get to curve sketching, but I'm going to have help session every morning starting Thursday. So um, so Thursday, 7:30, Friday, Monday, and Tuesday. All right, any last minute questions? All right, I'll send out a reminder this afternoon about that I'll be checking homework for 5.6. But I'll see you guys tomorrow. Have a great day, guys.
Thank you.
Thank you. Bye.
Mr. Yang.
Yeah, what's up?
Sorry, I had a question about
Uh-huh.
number 3.
Uh-huh.
So for number 4 and 5, I followed the same, like I did 10 like you did, and I got the right answer. But for number 3, I did 10 again. And I thought you were saying I could like pick any sign, but then I ended up getting the
Well,
wrong
yeah, so the
answer.
thing is, sometimes we're restricted to what we can use, especially if we don't have enough information on one side. So in this
Okay.
case, for number 3, we're not provided any information. I mean, I guess we can find the length, but we have no way of finding the rate of change of y. So because of that, we're kind of restricted to having to rely on x, because we have dx dt, but we don't have dy dt. If we don't have dy dt, we're kind of lost, with a variable that we don't have information for.
Okay. Wait, so but I was curious because when x equals 6, right? I thought technically then you know that y equals 8. So then I
Yes,
just
y
did
equals
x
8,
over.
but y is it's a changing value.
Oh.
So there's a dy dt, but we don't know what dy dt is.
Okay,
But
so that's why you just avoid that.
yeah, but we do know the hypotenuse is 10, and it's a constant, so nothing
Oh,
will
okay.
change
So when it
about
gives
that.
you the value, that means it's constant. Like
That's
if
right.
it's
If they give you the value, that means it's constant.
okay,
Especially
so
if
that's
it's in
why
a
I want to use
diagram.
that.
Yeah, if it's in a diagram, then it's definitely a constant.
Okay.
But then sometimes if it's a word problem, then there should be enough context clues to tell you if they want the hypotenuse to be constant, they're going to give you enough information to say that it's constant.
Okay. So for some of them, you could use any, but
That's right. That's right. Yeah, good point. Some of them you can use all three equations. Others are restricted based off the information in the problem and is forcing you into one trig equation.
okay. All right, cool. Thank you, Mr. Yang.
Okay. All right. Have a great day. Thanks, Pierce.
Bye. You too.
Bye.